Sometimes you talk with people about waves and they talk about things being sort of in phase with one another and out of phase with one another. I want to make sure that we understand what this means. If I have two waves that are in phase with one another, we're talking about these. I'll put a box around it so you can tell these pictures go together. We're talking about two waves that are synced up with one another. These two waves are all synced up. Our math teacher friends might talk about them not having any horizontal translational shift relative to one another. Can you imagine our math teacher friends saying something like that? No horizontal translation. So not horizontally, horizontally shifted with respect to one another. Now, if two waves, by the way, if you have a bunch of waves that are not horizontally shifted with respect to one another, we say that they're a coherent set of waves, but that's another, I'm not going to introduce that right now. But the lasers, by the way, are coherent waves, right? Like all the waves are in sync with one another. That's kind of a neat thing about lasers. Anyway, these guys are not phase shifted relative to one another, but if these waves are in sync, then they create constructive interference with one another. They just superimpose. You can't have just one wave or the other. If they're at the same spot at the same time, they superimpose. However, if they're 180 degrees out of phase, put a box around these guys just to show that they kind of go together. When I say 180 degrees, this actually looks like a vertical flip. You see what I mean? This is not a vertical flip. When with waves, because it's a continuous function, I'm going to extend this out a little bit. And if I go over it in pink, this guy here in pink, this guy here in pink, can you see rather than it being a vertical flip, those two waves are actually just thrown out of sync by half a wavelength. Okay, now if you're a trig person, you say, oh, they've been thrown out of phase by 180 degrees, like sine wave, cosine wave. If you're a physics person, you might say they've been thrown out of sync. They've been phase shifted by half a wavelength. Synonymous, right? Same thing. So I'm going to put that in writing. I'm going to say when two waves are shifted by 180 degrees in math class, or half of a wavelength, that's lambda divided by 2 in physics class. You guys talked about radians yet?
Yeah.
It depends on the math class you're taking. If you're taking a math class that's talked about radians, then you'd say, ooh, is it pi radians phase shifted or 2 pi radians phase shifted? Pi. You know your pi radians. Yeah, it's phase shifted by pi radians. I'm not going to throw that in yet because that's not something that we know about. Oh, let's put it in. Let's lean into the mystery. So we'll say pi radians in advanced math.
Advanced functions.
Yeah. Okay. And those of you that haven't gotten to radians yet, you will. But we've got this wave that's been phase shifted by half a wavelength. And so that's what we're going to focus on in this class, is to talk about it in terms of a lambda over 2 phase shifting. And when those waves are out of sync, then you get destructive interference. Now, if I have two sound waves that are in sync, constructive interference, this would be a loud sound. What would this sound like? Silence, right? And it always struck me as odd that you could have two waves making vibrations. And yet when they meet up, if they're 180 degrees out of phase or half a wavelength out of phase, you hear nothing. But this guy right here, this phase shifting idea, leads into noise canceling headphones. All right. I want to be a little bit less curvy and a little bit more geometric here. I got two triangular waves that are 3.5 units tall. Let's just take a snapshot of what that looks like, okay? So 1, 2, 3, no, 1, 2, 3. Maybe I can start from here. 1, 2, 3. Yeah, 3.5. Maybe I'll draw a ruler line. Really faint. All right, so I've got my ruler line in there. 1, 2, 3.5. It doesn't tell us how wide these things are. Oh, shucks. I can't do it that tall. I'm going to have to put my ruler line all the way down here, I think.
They make it like about 7 units tall.
Yeah, I'm just realizing as I'm doing this, I got to think this out a little bit better. 1, 2, 3. I'll have to put the top of my triangle here. 1, 2, 3. Top of my triangle here. Let's make this triangular wave be 4 units wide at the base. I suppose it's not a true wave, it's a pulse. Okay, so I've got a triangular pulse and another triangular pulse. Now, it's common in physics class to talk about geometrically shaped pulses. Now, of course, sound waves typically take on like a curvy shape. We even saw with a graph of my own voice in an earlier lesson that it is kind of a complicated curvy shape with superposition. Basically, geometric waves are easier to draw. And so we're going to learn the basics with the geometric waves. What does a geometric wave sound like? Actually, if you ever listen to old synthesizer music or pop electronica, it sounds like that robotic sound that you hear in old synthesizer music. Those really are geometric wave shapes. That's why they sound unnatural. A human can't make those sounds, okay? So there is a sound to it if you listen to old synthesizer music. Anyway, when these two waves meet up with each other, how tall are they going to be? 7. Yeah, look. We can make one be pink and one stay blue. But when they get to each other, when they meet up with each other, and they totally superimpose with one another, total superposition, the resulting waveform is going to be 4 units wide, just like the original two were 4 units wide. And it'll be 1, 2, 3, 4, 5, 6, 7 units tall. Now, if you're somebody who's really into actually drawing these shapes, like by adding them up, look, we would have, I'll do it in dotted lines. I would have this dotted line. This would be this pulse. And then I would have a second dotted line. Let's make this one be red. They would be at the same spot at the same time. Maybe it's a little bit tricky because they're the same size. But I'd be adding up the red dotted line and the blue dotted line to give me the solid resultant wave for that moment in time. I got another one. This next one says that I've got a triangular wave that's 5 units tall, and it met a triangular trough, and a triangular peak. So a trough is like a low down, a negative pulse, and a peak is a positive pulse, okay? Now it says that it's 5 units tall. I feel like I'm looking at this page, and I'm not sure that I have a properly scaled grid. Can you guys see that I'm only going to have 4 above and 4 below? So why don't we make like a little swap out for ourselves? Let's make this 4 units tall. Only just because my grid doesn't satisfy the requirements, and I don't want to do a scaling issue with this one. So if I was going to have a triangular trough, let's again make it be 4 units wide. So we have our trough. You know, something that I messed up with the previous one is that we should give ourselves pulse direction vectors. So they're traveling towards each other. So here I've got my trough. It's going this way. I've got my peak. It's going this way. And if we want to be all color-codey about this again, we can make the one on the left be red, and we can make the one on the right be pink. But that means that when they get together, and they're totally superimposed, 4 units wide, that At this moment in time, I would have, I'll do it in dotted lines because it's not actually there, my triangular trough, and again in dotted lines because it's not actually there, my triangular peak, and the resulting waveform would be total destructive interference. Oh, of course I got a simulator for this. Pull this over. Oh, it was running. What happened to this? Try that again. Grab it over. All right, well, it looks like the simulation doesn't want to load for me. That's okay. Maybe it'll be happier with me later. Anyway, all right. All right, so we have this next question. What did the two pulses look like that created this interference pattern? Oh, man, I got it. Now it's back again. All right. So let's see. Whoa. That's wild. Look at this. I got one wave that looks like an M, another one that looks like sort of a right angle triangle. And they pass through each other. There's the total superposition. I got to be careful. Look, where the vertical line is, isn't it the same height on positive and negative? So it's going to cancel each other out down below here. Notice these are stacked graphs, right? So the resultant graph is at the bottom of the screen, and the original two is up at the top. If I slice this one here vertically, this one has an amplitude of positive 3. At the same time, the other one has an amplitude of negative 3. So again, canceled out. Now this one here, sliced vertically, positive 2, negative 2. So 0, still canceled out. But by the time I get to this slice here, notice that it has an amplitude of positive 3, and this other one has an amplitude of negative 1. So it adds up to positive 2. And by this slice here, the earliest part of it, amplitude of positive 4 and amplitude of 0, so the resultant is just positive 4. And we can try this with anything. Try out another one. Like I got this square one here. Oops. Well, let me, I have to drag things around. Ooh. All right, so this would be like a square graph plus a triangular graph overlapping with each other. So with this idea in mind, I want to come back over to my static page version. If this is what they looked like when they were totally superimposed, what did the original two waves look like? Here's my original medium. I'll just draw it as a straight line. Anybody want to suggest what the original two pulses looked like? Yeah? A square. Are either of them negative? Yeah, we got a positive square traveling towards an equal width negative triangle. Not only equal width, but can you see it must be equal in height to the square? And people say, well, how would you figure that? Well, hey, if I have this square and I have a triangle, and I then take slices, like I was mentioning with the animation, I can slice it. I can say, the amount that it goes down below the principal axis here is equal to the amount that it goes up above the principal axis here. So that would be the resultant for that slice. This guy here, I would take this negative amount away from this positive amount. That slice. 0 on the triangle taken away from the top corner of the square, and symmetrically the same. And then I really do a curve or a line of best fit. And for geometric waveform superposition, it ends up being basically connect the dots, right? And if I take that line of thinking, what would it look like if I had a wave that looked like this on a collision course with a wave that looks like this?
House.
First answer is, hey, looks like a house. Yeah. Graph paper.